Our universe is expanding. In fact, it has been ever since the Big Bang, 13.8 billion years ago. The initial event taking only a fraction of a second to get started. After this, gravity would take hold and begin to slow the expansion of the universe down, in what would come to be a futile effort to hold matter closer together. This slowing by gravity would go on for 9 billion years. After this, however, there was a shift in the paradigm. Rather than continuing to slow down, the expansion began to speed up, driven by an unknown force, which we will come back to later. First, we turn back the clock to the year 1912, when American astronomer Henrietta Swan Leavitt was studying Cepheid variables. These are a class of star whose brightness fluctuates with a regularity that depends on the star's brightness. All Cepheid stars with a certain period, this being defined as the time it takes to go from bright to dim, have the same absolute magnitude or luminosity, being the amount of light they put out. Leavitt measured these stars and proved that there was a relationship between their regular period of brightness and their luminosity. These findings made it possible for astronomers to use a star's period and luminosity to measure the distances between us and the Milky Way galaxy, from the observed Cepheid stars in their far-off galaxies. Around the same time in history, another astronomer named Vesto Slipher was observing spiral galaxies using his telescope's spectrograph. This is a device that splits light into the colors that make it up, much like the way a prism can split light into a rainbow. This was a relatively new invention at this time as well. With this piece of equipment, Slipher became the first astronomer to observe how quickly the galaxies he was observing were moving away from us. He did this by observing redshift in these distant galaxies. Now, when an object is moving away from us, its light gets stretched out on its way back towards us here on Earth. In this instance, light's behaving like a wave, and light that has redshifted has basically been stretched into the infrared part or wavelength of the electromagnetic spectrum. These two discoveries would play an important role in astronomers' ability to observe and determine that galaxies were getting farther away from us over time, which directly showed us how the universe was expanding. In the years that followed, different scientists around the world would start to put the pieces of an expanding universe together. All of this would come to a head in 1929, when we would receive full confirmation that the universe is expanding, by none other than Edwin Hubble. He did this using observations from his associate astronomer Milton Humason, and it involved the two discoveries I mentioned earlier. Humason first measured the redshift of spiral galaxies. Then, both Hubble and Humason studied Cepheid stars in those galaxies. Using the stars, they were able to determine the distance of the galaxies they were in. They compared the distances of these galaxies to their redshift, the redshift of their light coming towards us, and tracked how the further away an object is, the bigger its redshift, and the faster it is moving away from us. With this, they found that objects like galaxies are moving away from the Earth faster and faster the further away they are, at upwards of hundreds of thousands of miles per second, an observation that is now known as Hubble's law. And so with this, the universe was confirmed to really be expanding. By this point, we had determined for sure, right, that the universe was expanding. But our story does not end here. Like I mentioned at the start of this video, scientists previously thought that the universe's expansion would likely be slowed down by gravity over time. An expectation that was even backed up by Einstein's theory of general relativity. However, this would all change in 1998 when two different teams of astronomers were observing far-off supernova. Now, you might be wondering, what exactly did they find? These groups, led by astronomers Adam Rees, Saul Perlmutter, and Brian Schmidt, noticed that at a certain redshift, the stellar explosions were dimmer than they expected. While this may not seem like a major find at first glance, these astronomers were looking at Type 1a supernovae, which are known to have a certain luminosity. This gave them a point of comparison for what they were observing. So, they knew that there must be another factor making these objects appear dimmer. So they took to figuring this out. Using the object's brightness, the researchers determined the distance of these supernovae, and using their spectrum, they were able to find out the object's redshift, and therefore how fast they were moving away from us. They found that the supernovae really were not as close as expected, meaning that they had traveled further away from us than we originally anticipated. It was these observations that led scientists to ultimately conclude that the universe itself must be expanding faster over time. While other possible explanations for these observations have been observed, astronomers studying even more distant supernovae or other cosmic phenomena in more recent years continued to gather evidence and build more support for the idea that the universe is indeed expanding faster over time. This phenomenon is now called cosmic acceleration. As scientists build up a case for cosmic acceleration, they also ask why. That's one of the big facets of science, right? Why is this happening? What could be driving the universe to stretch out faster over time? This brings us back to the unknown force I mentioned earlier, which we have taken to calling dark energy. But what might dark energy be? Well, the truth is, right now, we are not entirely sure. Dark energy is just the name that astronomers have given to whatever the thing causing the universe's accelerated expansion is. It has been described by some as having the effect of a negative pressure that is pushing space outward. While we don't know what it is yet, there are many ideas floating around about what dark energy could possibly be. And today we will be covering some of them. It is important to note that for all of our guesses, the answer could just simply be something else entirely. Now, some scientists think that dark energy is a fundamental, ever-present background energy in space known as vacuum energy, which could be equal to the cosmological constant. Okay, the cosmological constant is a mathematical term found in the equations of Einstein's theory of general relativity. Originally, this constant existed to counterbalance gravity, resulting in a static universe. But once Hubble confirmed that the universe is actually expanding, Einstein removed the constant, citing it as one of or his biggest blunder. But then we made the follow-up discovery that not only is the universe expanding, but it is accelerating as it does so as well. This has led some scientists to suggest that there might actually be a non-zero value to the previously discredited cosmological constant. They suggest that this additional force would be necessary to accelerate the expansion of the universe. This theorized that this mysterious component could be attributed to something called vacuum energy, which we mentioned earlier. The theoretical background energy that would permeate all of space. While this theory has been a popular topic of discussion, it has been calculated that in order for there to be enough vacuum energy in space to account for the accelerated expansion, that during the beginning of the universe, it would have caused it to expand so quickly and with so much force that no stars or galaxies would have even been able to form. And, as we are here, studying this in the first place, we know that is not the case. Meaning that if it is in space, there must be less vacuum energy in the universe than the predictions came up with. And this discrepancy has yet to be solved. It has earned the name the cosmological constant problem. Then we have something known as quintessence. I think a pretty cool name. Some scientists think that dark energy could be a type of fluid or field that fills space and behaves in an opposite way to normal matter, and can vary in its amount and distribution throughout space and time. It has been suggested by some that quintessence could be like a combination of dark matter and dark energy, though these two things are currently considered to be completely separate and different from one another. In these two cases, by our current understanding anyway, these energies or forces would have needed to be weaker than gravity in the beginning of the universe, but then overtaken it later on, thus leading to the accelerated expansion. And while this is totally possible, it really does make me wonder if there is a flaw in our current understanding of the universe and its development. It is always important to remember that things we have discovered may not always encompass the whole story, which leads us to what some scientists think, that dark energy is not something physical we can discover. Rather, they think it could be an issue with general relativity and Einstein's theory of gravity, and how it works on the scale of the observable universe. With this explanation, scientists think that it's possible to modify our understanding of gravity in a way that explains observations of the universe made without the need for dark energy to kind of make them work. We have seen this sort of thing before in history. Newton's laws of gravity could not tell the whole story, but at the same time they were not disproven by Einstein's theory of relativity. They were instead encompassed in it. So the case could be the same here, where Einstein's theory can no longer tell us the whole story, but that they will be encompassed in a greater, larger one that can. Dark energy may be one of the great mysteries of the universe, but we are in an era now where we have tools powerful enough to put known theories to the test, and really investigate the big question we kind of posed and touched on earlier. What is dark energy? We already have telescopes out there, either orbiting or planned to launch, that are studying this. Many of the same ones that are also looking at dark matter, such as ESA's Euclid Space Telescope and NASA's upcoming Nancy Grace Roman Telescope. As I covered in my dark matter video, which you can find here, Euclid and the Nancy Grace Roman will both achieve this by making a 3D map of the universe, spanning across space and time. With this data, we can then try to see how matter has been pulled apart by dark energy over time. The map from Euclid, for example, will include observations of billions of galaxies found up to 10 billion light years away from Earth. Roman will allow us to take a look at how matter in the universe is structured and has spread out over time, to possibly see how dark energy has behaved and changed during that time. It will also conduct an additional survey to detect more Type 1a supernova. NASA even has a citizen science project called Dark Energy Explorers, which enables anyone in the world, even those of us who have no scientific training, to help in the search for dark energy answers, which for me is particularly exciting. So to conclude, like dark matter, we don't know what dark energy is, but we are fairly certain that it is there, or is possibly a hole in our understanding of the universe. And our current steps of trying to understanding both of these is to start by observing the effects that they have on our universe. I, for one, am excited to learn more about this mystery for dark energy, and I'm happy that we all have an opportunity to help out with the search and maybe make a difference as well. What do you think dark energy is? Do you have a favorite guess on what it is so far? I would love to hear more about this in the comments below. And I implore you to step outside tonight and look towards the stars.